we introduced the whole idea of calculus and differentiating. And what's this idea with a gradient function, right? We took a while to do that. We drew fun pictures of apples and moons and that kind of thing. Then we started to get down to brass tacks with the whole idea of differentiating, right? We sort of developed two, if you like to call them, rules for differentiating. We looked at things that you can differentiate, which are like polynomials, things with powers on them, right? Or you can slap a number out the front, all that kind of thing, okay? We looked at those. We looked at what happened when you took a function like this. Let's say, I don't know, I've got x squared minus 1 over there. And then you raise that to a power. So it's like this, but on steroids, right? So you chuck an n up there, okay? And we called this, we gave it two names. We called it chain rule or function of a function rule, right? So this is great. These will help us to deal with these kinds of functions, but there are lots more kinds of functions. And so we introduced lots more kinds of rules to deal with them in a quick way, rather than always going back to first principles, which is tremendously inefficient, very time consuming, okay? So that's my sort of preamble for, we're going to learn this. Shortly we're going to learn the quotient rule as well. Why are we learning all these rules? It's a pain trying to remember all of them. The reason why we learn them is because it's quicker than going back to first principles and always doing that. Okay? So, product rule. Thank you. We're going to start with an example that we could do without product rule, actually so that I can demonstrate why we need product rule. Okay? So here's a function. How do you differentiate it? If I was saying work out dy on dx, okay? Or another kind of a notation that I introduced in our first lesson was y dash, which is shorthand for differentiating. What would you do with this? Okay. Now, I know we can expand it out and treat it like normal. Okay. But for now, I just want to imagine. Well, it's a product of two other functions, right? So, would it be unreasonable to think? Okay. If you've got a function here, let's call this part f. Okay. Actually, I might call it u instead, because that's what I'm going to call it later. Got a function there, I'm going to call it u. I've got another function here that I'm multiplying by, and I'm going to call it v. Okay. If I want to find y dash, and I've got u times v, it wouldn't be unusual to think, can I take u dash and v dash, right? Differentiate each one and then multiply them, right? So I'm saying, maybe, the derivative of a product, okay, would be the product of the derivatives. Okay, let's try this. Let's see what happens. Let's consider if, I'll put it in red. Okay. Let's consider if y dash is equal to u dash times v dash. Okay, I'm going to differentiate each one. What would happen? What's the derivative of x squared? Just 2x, yeah? Bring the power down, reduce the power by 1. And the derivative of x squared minus 1 is also the same, right? Because that minus 1 off on the end, you differentiate it and it just disappears. Okay? So my result here is 4x squared. Okay, 4x squared. Now, if we didn't know any better, we'd say, well, it seems legit, right? Why not? Okay? But you guys know, you're probably already sort of doing the numbers, this is a little suspicious. For starters, the degree of this, right? The degree of this polynomial is, what's the degree? It's 4. And when we differentiate things with powers, right, we expect them to go down by 1. So if the degree is 4, we would expect the derivative to have a degree of 3. But I've ended up with 2. What's going on? Okay. So, sure enough, let's expand it first and then differentiate with the rules we already know. Okay, so, let me get rid of a duck. And get rid of this, because it's wrong. Okay. And let's expand it out. Okay. So, I'm going to first consider y as x to the 4 minus x squared. You happy with that? It's just an expansion. So now when I take dy dx, y dash, okay, I'll just do each one in turn. And you get 4x cubed minus 2x. Okay? And what you can do is you can graph this, it's quite easy to graph, and you can verify this is the pattern that the gradient function follows. It's not just 4x squared, that's way too simple. Okay? So therefore, when you're dealing with products, you can't just simply differentiate each one and then multiply them together. We need to introduce a way of, well, how would you come up with this without expanding? Like here it's easy to expand, but what if it was a disaster to expand? What if it was something like x to the 4 and x squared minus 1 to the 7? Okay, so there's a chain rule in there. I don't want to expand this. What a pain. Okay, so what can I do with it? Now,